Okay, Margaret, I'm going to talk about solids, and I hope this helps your understanding a little bit. I'm not 100% sure what's on all these slides, but I did this last year, so they probably should be pretty good. All right, this is about the solid state. Basically, if something is solid, it's either it's crystalline. Let's see if I can get this correct. It's either crystalline, which basically means you have a regular order of atoms or molecules, and they form a pattern. Um, you could think of something silly like this as a pattern. And if it's repeating in all directions, you call it a crystal. And it says the entire three-dimensional array is called a lattice. Things are amorphous if they don't have that long distance arrangement. The classic things that are solids in our world that are amorphous are glass and plastic. You don't have a regular arrangement of things. All right, so some crystals form very slowly in the earth. So a lot of the things that we make jewelry out of, or the crystal that you buy at the store to have fancy glassware for tables, the arrangement of the atoms is very, very regular and very beautiful. People like crystals. Here's the concept of what we mean by a unit cell or a lattice. This is two-dimensional, this is three-dimensional, but in both cases, I think you can see that even if you have a crystal that has millions of these boxes, you could break it down to the smallest possible box. So this one here, they call it a unit cell. So that box is repeated in all three dimensions. So left to right, up to down, front to back. This is a two-dimensional lattice, and notice that the unit cell here has some angles in it, because you might say, oh, well, can't you just make the black box the unit cell? No, because if you don't really repeat the black box in all the directions, you repeat a mixture of black and red. And so this is the smallest version that you could come up with, and you could just basically slide it in any of these directions and get the same thing. Notice how I did that on an angle. You might say, oh, can I just take these two boxes and slide it up and down? And the answer is no. You can't repeat the black on left, red on right by just slipping it down one slot. You got to do it with the angle. I did. I accidentally skipped the simple unit cell. The simple unit cell only has atoms on the corners, and notice that they touch, and the coordination number in a simple unit cell is 6. So a simple cubic cell has 6 nearest neighbors along these edges here. That's what you see in the picture. There's only one atom per cell. 1/8 of each of the corners contributes to that cell. All right, so in Gen Chem 101, or 103 in your case, we really only look at cubic unit cells. So a cubic unit cell is a repeating unit that has the same length on each side. So the height, the width, and the depth are all the same. And so I'll just use the letter A to represent that. What this shows you is a body-centered unit cell. So you have a unit, this is kind of space filling where the atoms are so big they actually touch each other. But the atoms on the corners contribute 1/8 of themselves to inside the box. And then that purple guy in the middle contributes its whole self in. So what this is telling you is that in a body-centered cubic unit cell, there's actually 2 atoms per box. And the blue ones, again, they can simultaneously be part of different boxes, which you actually show here. You see that blue atom on the corner there? Even though only 1/8 of it is inside the blue box, the other 7/8 are spread out over the other boxes. The definition of the coordination number is for this atom that you see in orange there, it has 8 near neighbors that are all the same distance, that are the closest nearest neighbors. So for each blue atom, the purple atoms are the closest nearest neighbors because they're actually touching, which you can see in this picture here. They don't touch along the edge, so the blue atoms are not the nearest neighbors of each other. And I already did this, and you have 2 atoms per cell. And then the final cubic cell that we talk about is called the face-centered cubic cell. I like to think of it as like a dice, which only has a 1 on each side. It's got like a dot right in the middle. So that's what they do with these green ones. So again, you have the corner atoms. You have 1/8 times 8. And then there are 6 faces on a cube, and each of them has half of the atom on the inside. So the total number of atoms in a face-centered cubic cell is 4. The coordination number is 12. It might be kind of hard to see on this picture, but you can see these 4 up here, these 4 here, and these 4 here. They're all the same exact distance from that central atom. This is probably, these 3 slides are a good thing to memorize. All right. What this picture is trying to show you is what happens when you have different layers of the atoms and what happens when they pack each other. So what they have here is a full layer of atoms, all like soldiers in rows and columns. What if you put an atom, a second layer, directly over the first? What do you get? Well, that's how you make a simple cube. And they do a calculation to show that in the cube, only 52% of this volume is occupied by atoms, and that means 48% is empty space. The way that you would do that calculation is you find the volume of the cube, and above that you would put the volume of one atom times 100, and that's how you get 52%. Now what's interesting is if that second layer was not directly over the first layer, but it kind of sat in the indentations, that's what you have here. So the green is sitting in the indentations. And then the third layer is over the first. That is what a body-centered is. Again, the green one's in the middle, and then you have the other atoms on the corners. If you had to do that calculation that I did earlier, you would do the same thing here. You would do the volume of 2 atoms over the volume of the cube times 100. And you would need to know some data there. Remember, the volume of an atom is going to be the volume of a sphere. So I think it's 4/3 pi r cubed. That's the volume of the sphere. And then the volume of the cube is just going to be the edge cubed. Okay? So for the body-centered, it would be 2 times the volume of that sphere. That's the volume of 2 atoms. For the simple, it would be just the volume of 1 atom. So it says here, notice how it would not be possible to create a second layer of the same size marble sitting in all the indentations of the first. So what you see here is a single layer. When I was talking about having them sit in the indentations, and let's say you put a second layer in there, you'd have to go over to here, and I'm sorry, made a mistake. You'd have to go here, here, and here. You could not put marbles in each of the 6 indentations because they would bump into each other. So what that's saying is that you could have a third layer which would be over the other one. And so that would be like what we call an ABC layer. So the one that I just showed you before, this is not the body-centered. This is what's called cubic closest packing. You have an AB layer that actually gives a unit cell which is not cubic. The hexagonal unit cell has these angles in it, but the cubic unit cell is ABC, ABC, and so they're trying to indicate that here. Notice you could study the bottom layer is the brown, the green layer sits in the indentations, and then where you put the third layer, you've got a choice. That's what this is trying to show you. You could either put it directly above the first layer, that's these places where it's colored in brown, and that would be the ABA layer. If you put the blue atoms in the open spaces that you could see through to, that would be the ABC layer. And it turns out that if you tilt the ABC layer on its side, you get our face-centered cubic, which we saw earlier, 4 atoms per cell. Notice that this is the most efficient packing of all. 74% of the volume is occupied by the atoms. And again, how do you calculate these occupation values? Here it would be 4 times the volume of one atom over the volume of the cube times 100. That's how they get 74%. Many of the metals that you see in just everyday life have these crystal structures. So copper wire has the cubic closest packing. That's the one that's the ABC, the face-centered cube. Same thing. Magnesium is a metal that does the hexagonal closest packing. That's the ABA. So this is not cubic. You can tell that. Look at this unit cell. It's got angles in it that aren't 90 degrees. This is a perfect cube. They are considered both crystals, but this is kind of a not the same family. Here's the math I was telling you about. There's a connection between what the edge is of the cube and the radius of each atom, and that's basically laid out here. So they use the capital letters to indicate the edge length. So for the simple cube, A, the edge length, is exactly equal to 2 times the radius of the atom, because notice, they touch along the edge. The other cubic families are a little bit more complicated. So the body centered, again, they use the letter A to represent the edge length, but you need to do 4 over the square root of 3 times R. That's the, again, that's the radius of the atom. The way that it's calculated is does this little derivation here. I don't know if your teacher wants you to know that. We don't make them do that. We make them just use the bottom line. For the face-centered, and I don't know if they give you these equations or if you have to memorize them, but the edge length, which is A, that's going to be equal to the square root of 8 times the radius of an atom. So I've seen problems in Gen Chem books where they give you the radius and you have to figure out, let's say, the edge length, or they give you the edge length and you have to figure out the radius. Always remember, though, that the volume of the cube is just simply A cubed. So they might even give you that. If they give you the volume of the cube, you want to take the cube root to get A and then solve for R. So I'm sure you could find problems in your book that are just that. Here's an example. It says copper adopts cubic closest packing. Cubic closest packing, that's the ABC, that's the face-centered cube. The edge length is 391.5 picometers. What's the atomic radius? Well, we gave you that formula on the last problem. Basically, do I have this here? That's the one I thought that was square root of 8 times R. Yeah, I think basically you could just plug that in. Let me see that here. So they gave you 361.5 picometers. Yeah, I got 127. I don't know why they made it so hard. But basically, if you know this equation, you can do it. All right. Barium is the largest non-radioactive alkaline earth metal. It has a body-centered cubic cell and the density of this. What is the atomic radius of barium? Okay, so this one made it a little harder. The atom is spherical, so we can find its radius from its volume. If we multiply the reciprocal of density by the molar mass, we can find the volume per mole of barium metal. The metal crystallizes in a body center cubic, so 68% of this volume is occupied by 1 mole. So let's see what they did here. I think this problem is too hard to worry about. All right. If you want to take a look at it, you can. You might wonder, how do they figure out these crystals? You can't put them in a microscope and know the distance. Basically, they use X-ray crystallography. And basically, the X-rays come in as these waves. When they hit an atom, they bounce off. And you could actually look at the pattern on film of the reflected light and work backwards and find out what the distance is or the angles between atoms. So we don't really spend a lot of time on that, but it kind of looks like this, and it's pretty cool. You could see a molecule that's super, super tiny and figure out the pattern of the atoms by looking at the diffracted X-ray. All right, so I know that you did this on a homework. Types of crystalline solids. Atomic solids consist of individual atoms held together only by dispersion forces. And so those are going to be just elements. So if you think of helium or atomic solids, neon, if you froze these things, they would be held together only by dispersion forces. Molecular solids are individual molecules held together by a variety of forces. So you can think of water or CO2 or ammonia, anything, or propane. These are all individual molecules that they condense into crystal structures in which each of the lattice points is not an atom, but a molecule. Ionic you learned about a long time ago. That's when you have a metal and a nonmetal, or you have one of those polyatomics. So something like ammonium carbonate, or sodium chloride, or barium hydroxide. You have cations and anions that combine to give you an ionic solid. Metallic solids, we already talked about, copper or cobalt or manganese or iron. And then network, basically this is going to be like quartz crystals, that's SiO2, or diamond, or graphite, carbon. Those are net. I'll show you some pictures here, I think. Oh no, first we're going to talk about properties. Usually atomic solids have very weak forces between them, so they're soft, they're very low melting points, they're poor conductors. Molecules have moderate, depending on the interactions between them, and they're not good conductors. They have things like maybe dipole-dipole and hydrogen bonds. Ionic are very strongly held. You'll see that you have really high melting points. Look at these numbers here. Metallic, it could range. You could have some soft metals, you could have hard metals. They definitely conduct electricity, obviously. And network, like quartz and diamond, very high melting points, very hard, usually poor conductors. Here's some other examples. If you look inside here, you'll see that they correspond to the thing I said. This is basically just some stuff that you should know. This is kind of like memorizing. I don't know if you have time to make flashcards or something like that. What does it look like when we say we have a crystal structure? Well, like I said, you could have each, this is a case of a face-centered atomic solid. So these are argon atoms frozen in place. You could also have a face-centered unit cell where each space is not an atom, but a molecule. So that's what they're showing you here. Methane, which is CH4, and it's attracted by dispersion forces, does crystallize into a face-centered cube, just like argon does. These get a little bit complicated because what this is saying is that the chlorides occupy the corners and the faces of this very large unit cell, and you've got the sodiums, or these tiny little guys that are along the edge. You could actually figure out the chemical formula based on how much these ions contribute to the whole unit cell. So let's look at the chlorides first. So the chlorides, you have 8 times 1/8 on the corner atoms, and then I have 6 face atoms, and each one of them is contributing 1. So these are the face. So there's a total of 4 chlorides in my unit cell. How about the sodium? This one's a little harder to see, but you've got a sodium all by itself in the middle, so that's one full atom. And then you've got a bunch of atoms on the edges. The edge contribute 1/4. That's easiest to see here. 1/4 of a sodium atom is inside. And I've got a total of 12 of those guys. So 4 on the top, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1 plus 1/4 times 12 is 1 plus 3. I have 4 sodiums. So notice that the simplest whole number ratio is 1 to 1, and that's why we call salt NaCl. There's 1 to 1. This is a different crystal structure in which the formula is ZnS2. See if you can figure out why that is. Did I get that right? Oh no, I'm sorry, it's just ZnS. It's a 1 to 1 ratio. Aha, this one is a 1 to 2 ratio. So here I have calcium fluoride. If you look, the calciums, you've got 8 of those. No, I'm sorry, you've got 8 of the fluorides, and you've got 4 of the calciums. So that's how you get Ca. This is basically just saying the strength of the crystal is going to be directly proportional to the charge that's on the top and inversely proportional to the distance between the atoms. So if you have really, what would be the strongest lattice energy? It's going to be small, high charge. Weak, large, low charge. Here's some evidence of that. Look at the smallest lithium fluoride. Its lattice energy it's very difficult to break it apart compared to larger atoms like potassium iodide. Okay. I don't think we have time to go through this, but basically you could figure out what the lattice energy is by adding together a bunch of numbers like this. So this is just saying that if you don't know what the lattice energy is, you could use a combination of things like ionization energies and electron affinities. Basically, all 5 of these arrows that I circled are equal to the one big blue arrow. And they do that for you here. I don't know if you did that in class. I think I'm going to let you go, but you can look at the rest of this and see if it helps and ask me if any questions you have. All right? Bye.